morning.
All right, so today we're going to do all kinds of stuff. So let's see. So we're going to mostly do post-main sequence evolution. So we talked about how stars look, what the basic equations are, and now we're going to say, okay, now things start to fail. What does the failure mode of a main sequence star look like? Okay, so business. So numerical 6 was due on Friday. Most everybody got it done. So I'll go over that, and that's the last numerical assignment. Paper homework is due tomorrow night. Office hours will be tomorrow. Does 9:30 work for everybody? I was going to do it at 9, but then somebody said PPS or something goes till 9:30.
Oh, modern.
Modern goes till 9:30. So it's 9:30 to 10:30 works for everybody? Yeah?
Do we have another
Okay.
paper homework after this?
Yes, there will be one more.
Okay.
So there will be one more due on the last day of class.
Nice.
Before Thanksgiving?
No.
No, just
The last day of class. The
Okay.
last day of class before Thanksgiving is the midterm. Because per bullet point 5, I decided to not have class next Monday. I thought I would take Everett's leave and just not do anything.
Oh, that's amazing. Well, congrats.
Next
Okay.
week. So this is.
What if Dr. Hill's please?
So anyway, mostly my brain is full, and I need to get some papers finished that I need to finish, right? But really, everybody could use a break, and it's nice to have a break during Thanksgiving. And Thanksgiving is the best holiday because it's not overrun by corporate greed, and it's just about seeing your family. Right? So, all right. Editorializing about our society while I distribute astrophysics information. Okay, let's see. I will reschedule the readings. I was going to do it. You could see I thought that I was going to get it done before I had to start talking, but I didn't. So I'll re-up the reading section. I'll tell you now, the one on stellar evolution is going to be due right after Thanksgiving. So you got I'm going to assign it tonight, so you have plenty of time. It's not due for another week and a half. But the one on stellar evolution is chapter 13. It's mostly what I'm going to cover today, so the reading's going to come after the lecture, but that's okay. That way you can ask questions on stuff you've heard twice. Okay, so we're going to go through numerical 6. Where am I? Not on the right notebook. There we go. So I think everybody did reasonably okay on this one. So the basic idea of these numerical lectures are first to get you just putting code in your hands that isn't very stressful, so that you get some code experience with not only making code work, but making code not work and sucking up and suffering through the consequences of code not working. So, debugging is part of code, and it's a drag, but you have to learn how to do it. So the physics idea that we're getting at is relating temperature to color, right? So the whole purpose of this one was to write a function that gives me a color based on a temperature. So how that function worked, and there's many ways to do it. I did it with this filtery way because I think that talking about how filters work is a useful side project. So the first thing that I asked you to do was take the star data and just plot the B minus V color versus the effective temperature. And that should look about like this. And then label your axis. And in the second one, I said, write a function that returns B minus V from a black body. And the way we do this, I'll do it in a cartoon. And I apologize for the sound today. I left my microphone upstairs. So we have our black body, and the color is just the slope of this curve at this point, or the ratio of these 2 points. Let's talk about it like the ratio of these 2 points. So we have this point, which we call V, and this point, which we call B, for blue and visual. And we just need to get the B minus V magnitude. So we first get the B flux, which is just the integral of the black body, let's call it S, of lambda, times the filter, of lambda for the B filter. So this is like a Gaussian, and this is our sole function. We do this integral, we pick out just this stuff here. And we do the same thing for V. And I said that backwards, but you sorted it out. Right? So this is the effectively what we do. So we compute B, and then you compute V, the same process, S lambda T V of lambda. And then you just return B minus V equals, let's call this FB, and FB is minus 2.5 times the log base 10. I spent a good long while looking for this base 10 in office hours. At least one of you, I know, made this mistake. This has got to be log base 10, not log base E. And just saying log means log base E in Python. So log base 10. Otherwise, this 2.5 gets in your way. FB over FB plus the constant that is for the normalization. Okay, is everybody basically comfortable with this as an idea? Does anybody want to talk about what this color means or how I get it or what I should do with it? So this is basically what we're doing. So then you got to write a function. So here, my B minus V would look like this. So S is going to be a black body with a wavelength and a temperature. So the temperature is the argument to my function. And the wavelengths I'm just defining as a definite thing. We have the peak of our wavelength and the peak of blue and the width of blue. We have the peak of V and the width of V. And then we get our Gaussian, and we got our luminosity, and then we get our other Gaussian, and then our other luminosity. And then we return minus 2.5 times the log of the ratio. That make sense? Yeah. Are we good? All right. Then we just roll that over a bunch of temperatures. Oops, I'm on the wrong laptop. And you should get a function that looks like this. And if they were offset, you probably used the wrong log. That was the one error that I saw people do. But we can see that the curve that I got is this smooth red curve. And you can see that the effective temperature from my standard star is pretty similar, but there's a little differences. And the differences come from the atmosphere that we didn't model. So we modeled the bulk of everything just as a black body with a certain temperature. Okay. Does anybody have any questions about that one? I think we are good forever on that. So now I'm going to talk about this. So we spent the last 2 weeks, 3 weeks, talking about what's inside a star and what's right around a star. So we talked about a bunch of things, and I'm going to leave that. I'm going to leave this up there, but I'm going to do most of my talking on the board, just because I need to come back to this image a lot. So, what is this? What is this image?
A mess.
What's that?
A mess.
A mess. Yeah. What do we call this? What do we call this part here?
Main sequence.
This is the main sequence, right? So we have luminosity over effective temperature. And effective temperature, this is a little number, this is the log of the effective temperature, so this is 1,000 and a half, and this is 10,000, and it's increasing this way because history. That's fine. It would probably make sense if we did everything in the other direction. But we have the basic convention that bluer is a smaller number. And that convention wins here. Bluer is a smaller number. So this line here defines the main sequence, and we get this from our 4 equations from stellar structure and evolution. What we're going to talk about now is what happens when the hydrogen at the core starts to run out. Then what happens? So we have this kind of complicated dance. All of these lines do basically similar things. Let's look at this one. We're going to talk about this one. So it depends on mass. Why does it depend on mass? Because the burning rate depends on mass. The temperature gradients depend on mass. The composition doesn't initially depend on mass, but then it starts to depend on mass once the burning gets going because things burn a lot hotter. So let's review what we know to date because we're going to need a bunch of things. So I'm going to say all these things again, and And if this is all boring review, then you have a low threshold for boredom. But probably all of this should be just repeating the things that I've said. But not things that we've had a lot of experience with. So saying it again is helpful. So what do we talk about? We talked about the 4 equations of stellar structure and evolution, which I'm just going to schematically write down. So the 4 equations are continuity, so this just says this is the mass density relationship. There's force balance. This is the relationship between pressure and mass. There's the luminosity. And this is the relationship between the luminosity, density, and burning rate. And then there's the temperature equation, which relates temperature and, okay, we had 2 equations for this because there are 2 different things that a star can do. So if the temperature gradient is high, what's the star going to do?
Convection.
Convection, right? So the temperature gradient, so think about this as it's hot on the bottom. That means the gradient is high. That means it'll start to boil. So this will either convect or radiate. And we had 2 different equations for these, but this relates temperature, luminosity, and pressure. So we have these 4 equations, and these set up gradients across the star. So we have, if we look at things versus R, density goes down like R, temperature goes down like R, pressure decreases with R. All of the quantities are decreasing functions of R, right? Why? Because I have a bunch of mass pulling down this way, so my gravitational force is in this direction, so my pressure gradient has to be in this direction, so the pressure has to be decreasing outwards for the pressure gradient to counteract the force. And as the pressure decreases outwards, so does everything else, because PV equals nRT. Right? So what's going on? So one of the things in here is this nuclear burning, epsilon. So these equations are really nice. They tie together mass, density, pressure, luminosity, and temperature. And they're tied together by the burning rate and the equation of state. How does the burning happen? So the burning happens by 3 processes. One was the proton-proton chain, which I would like everybody to make sure that you can write down at least the PP1 chain, right? So that you can write down all those steps. It's not a lot of steps, but there's a couple of them. So the proton-proton chain takes a proton plus a proton, and actually you need 4 protons. And that turns into a helium-4 plus 2 positrons plus 2 neutrinos. But it doesn't happen directly. I'm putting that arrow in quotes because there's a lot of things that happen in there. So this is a several-step process. So we have the PP chain. And the energy generation rate for the proton-proton chain goes like density times temperature in units of 10 to the 6 Kelvin to the 4th. Okay? So those are the important bits that I want you to know about proton-proton chain. So I want you to know how all the steps work. I want you to know that the energy generation rate goes like T to the 4th. That's a very important part of the proton-proton chain. We also have the CNO cycle, where we have a carbon plus a proton gives me a nitrogen, which then gives me another carbon, which gives me then I get a proton, which gives me another nitrogen, which then gives me then there's a couple of ways it can go. Either you get an oxygen or you get a carbon. But you have this process where basically You take a carbon, you add a proton, you get a nitrogen. You add a proton, it beta decays back to a carbon. You add a proton, you get a nitrogen, and another proton, you get an oxygen. Thereabouts. You might have another beta decay in that. Then then you add another proton, and that oxygen turns back into a carbon and a helium-4. So you get so this process is a little closed loop. So the carbon, you get the carbon back, and you get a proton, or you get an alpha particle. So I want you to go through and make sure that you understand at least the first chain of this, at least the first step, because it's a set of several steps. And you need to know that the burning rate, epsilon, goes like T to the T6 to the 20. The book writes it as 19.9. A lot of people just round it up to 12. We also have the triple alpha process, which is helium burning. So an alpha particle is a helium nucleus, right? Alpha is just helium-4. And this process is another chain of things that of events that basically takes 3 alphas and makes a carbon. Which that makes sense, right? This is, I got a carbon 12, and that's 4 helium, 3 helium-4s. And this burning rate, epsilon, goes like T8. So this is temperature in the units of 10 to the 8. This is a hotter reaction. So you have to get hotter to get this reaction to happen. To the 41. How often do you see functions that go to the 41? Right? This is a very, very, very sensitive function of the temperature. Okay. Let's see. Those are the. So we also know the I, the S. I is the radiation field. So think about this as photons per second per geometry, whatever your geometry happens to be, equals minus kappa rho I plus a source term. Now, I didn't really go through this in much detail because the first part is most interesting. This is the interesting part. But also, you could just be making photons in the process, which we do. So what this says is that I, in the absence of source terms, I equals I naught e to the minus tau, where tau is kappa bar rho L, where L is the length of the cloud. This is an average. So tau depends on the density of the stuff, the size of the stuff, and this thing called kappa, which is a huge headache to get, and you have to spend lots of money to actually get it. I have this one experiment that I'm doing on a huge laser, and some of the data is classified because I'm not allowed to see the opacity of gold because it's classified information. There's all kinds of weird things. The opacity is really, because it was really hard to get by the federal government, by the nuclear weapons.
What if I did it?
What's that?
What if I figured it out?
Well, if you figured it out, then they would investigate you for blowing stuff up because it requires getting gold hot enough to glow, which means you're blowing some stuff up. So opacities, so they're so complex and they're so fussy and they're so fiddly that the government dumps huge amounts of money into sorting it out for various substances and then keeps that very secret because it's hard to get. So kappa is a headache, but we deal with these Roslin mean opacities, which works just as well as we could as we want, and it's good enough. So we deal with the mean opacity.
So we're not allowed to know kappa sometimes.
I'm not allowed to know it if you're allowed to know it. Okay, classified information is a funny thing. You're allowed to know it. You're just not allowed to tell anybody. You're not allowed to share information.
Do you know it?
What's that?
Do you know it?
Which?
The gold?
No, because it's classified, and I don't have clearance anymore.
Anymore?
Yeah, I had to give clearance when I left the lab. That's a whole other side story.
You should tell that side story
What
another
can you
time.
do with
Yeah. What's that?
what can you do with the opacity of gold?
You build a nuclear weapon.
Yeah, I was about to say, build a
So
bomb.
that's not the whole thing. So this is just a weird side tale of this. So they need to know the opacities of all of the pieces of the device because they need to know how the photons are going to get out. Right.
What do they use the gold for?
All kinds of stuff. Like gold is an incredibly good conductor,
Yeah.
and it's non-corrosive, so it's a very useful material. So I was using it. I know. I was using it for. You want to see something? Let's see.
Yeah.
Am I in a hurry? I'm not
sorry.
in a
You
hurry.
do
Not
real
say
over
this,
here.
and then you can't just say this and then not explain everything.
Yeah, like, and then we need to know the
And then we need to know the last part, just make sure.
Well, I was a postdoc at Los Alamos, so I worked there for a couple of years. And I got they wanted me to do code stuff. Let me show you real quick the why I needed it. Where the hell are my talks? Talks. Here's my job talk. So I have this project. So none of this is on the. Did that go on? There it is. Okay. This is my promotion talk. Wish you would have enjoyed. This, can you see how big this is?
It's big.
There's people down here. This is the test chamber for the National Ignition Facility, and this is the largest laser in the world. It takes 192 lasers that are about this big, and it builds them in this 10-story tall building that's like a football field long. It has this laser is the size of a football field plus 10 stories, and then it directs all of that energy, all of that laser energy, onto a very tiny capsule of deuterium. And what the purpose of the experiment is to take that deuterium and fuse it into helium. So it's a fusion experiment. But it's a huge laser, so you get to do other cool stuff too. So we have, I have this star formation project where we take this object here, and this is why we care about the gold. This is a little block of gold, and this is where we hit the laser. So the laser hits this block of gold, and the block of gold gets really, really hot. And what does it do when it's hot? What does anything do when it's hot? It glows. So what does something do when it's hot, like 10 to the 8 Kelvin?
No.
Goes white.
No, it sublimates straight into a plasma.
Ah.
So it melts like crazy, but what part of the spectrum, if it's 10 to the 7 Kelvin, what part of the spectrum is it going to radiate in? Yeah, it's in the X-rays. It's not quite to the gamma, but it's in the UV X-rays. So we get this enormous amount of light that then rips apart this thing, and then we have this little block of foam inside that we study the turbulence. So we have this thing that we blow up, and we study the turbulence in this. Why do we study the turbulence? Because I really want to study the turbulence of things like this. This is, which one is this? This is Westerland 2, which is a star-forming cloud. Boy, this projector's terrible. This one is Carina Nebula. These are star-forming regions. And these are all lit up by huge, bright OB associations of stars. So you have these huge UV flux impinging on this molecular cloud. And then the shock waves drive little fluctuations that form stars. So we want to understand how the shock wave forms little density fluctuations in the back of this shock so that we can understand how stars form. So, but to do that, we need to drive shocks through this little piece of plastic. And to do that, we need to light up this piece of gold. And since it's a nuclear weapons project in the first place, they're going to keep all the stuff that they don't want me to see secret. It's a funny process. So anyway, opacities. This is a long side story to say that opacities are very complicated and difficult to get and hard to understand.
And sometimes classified.
And sometimes classified because of the difficulty in obtaining them. Where am I think of? Oh, I was on the wrong slide the whole time. Should have showed this picture. Sorry for the video people. So okay, opacity. We're just gonna deal with opacity as kappa bar is gonna be like k naught t to the minus 3.5. This is Kramer's rule. So opacity is something that if you really get into stellar astronomy, you'll really go down the rabbit hole of opacities. it's a deep rabbit hole. For now, all we need to really care about is that the opacity goes like t to the minus 3.5. Okay. Let's see, are there other pointless random stories that I need to inject? I don't think I do. Okay, now the last thing that we know is that the star has a luminosity L, and L, or L over C, C squared, is the rate that it's losing mass energy, or L is the rate that it's losing binding energy. So this is the rate of energy loss. So things leave the star at that rate. So now we need to talk about, so if you say, all right, time is fixed, my density is not a function of time, my species fractions are not a function of time. So we have these species fractions, which I have not done a good job saying. X, Y, and Z. And this is the fraction of hydrogen. Y is the fraction of helium. And Z is the fraction of metal, which is everything that's not hydrogen or helium. It's a really easy classification scheme. So as long as these three things are fixed, then you just solve these four differential equations, and they give you the structure of the star. Then you let the star burn and see what happens. So we put these into a computer to really let everything happen. So now, let's see.
Yeah.
I know, we were talking about the opacity of gold.
I know they're on me. Yeah, I know all kinds of pointless classified things that I could tell you, and they wouldn't be distinguishable from the other random crap that I know. That is complicated and pointless.
You should just start sprinkling it in.
I know.
What's the most interesting classified information?
All of it. Really, none of it. It was all boring details. Okay, so let's talk about this picture here. So each one of these pictures has, so each one of these, so bigger stars are much hotter, right? That's one of the things we get from this. So 0.8 solar masses is down here, and 25 solar masses is up here, and this is a much hotter. So this has a temperature of 10 to the 3.7, and this has a temperature of 10 to the 4.7, so this is an order of magnitude higher in temperature. Being a higher temperature means that my burning rates go up a lot, right? So my burning rates can go up really substantially. So if my temperature is low, if I have a low mass star, it's primarily going to be burning through the PP chain. But if I have a higher mass star, it can burn the CNO cycle too. And when things get really bad afterwards, then triple alpha kicks in. But that's when things have to get really hot for that. So what can we say about CNO cycle just based on its temperature dependence? So I know that it's not going to show up for lower mass stars because their temperatures are low.
Is it faster?
It's faster, and it's more sensitive to the location in the star. Where is it going to live? Just in the center, because the temperature falls off really fast, so the process shuts off very quickly. Okay. So PP chain keeps most things alive. CNO is good for later on. Triple alpha kicks in when things get really bad. So, the other thing. One more thing on this big wall of knowledge. The other thing is the Kelvin-Helmholtz contraction timescale. So when they were first looking at stars, if you take Hydra with me, which I think I'm actually teaching next fall, if anybody's interested in taking fluid dynamics, it's a super fun class. we'll talk about another Kelvin-Helmholtz, which is about clouds. So Kelvin and Helmholtz did a bunch of cool things together. The Kelvin-Helmholtz contraction time scale is the luminosity over the gravitational binding energy. No, I'm sorry. I write this upside down every time. Okay, you gotta work through this with me just because I screwed up. I'm assuming that other people will too. L is E dot. L is dE dt. Right?
Yeah.
So if I want a time scale,
Is it E over E dot?
yeah. It's energy over the luminosity. This will give me the time scale to drain all the energy by that luminosity. Okay. That is everything that we know so far about stellar structure. It's quite a lot. So now what happens when things start to fail? When things start to fail, we have a couple of processes. So here's the main sequence. We're going to talk about this one. This is for a 5 solar mass star. So here's the main sequence. The first thing that happens is it moves that way, and then it moves this way kind of horizontally. Then it moves up and then back over horizontally, and then really up and then really back over horizontally, and then it falls down to become a white dwarf. Follow all that? So what are these processes that are going on? So let's first talk about what is it that sets where things are in this diagram is, sorry, there's a sigma and a pi and a 4, I think. So the luminosity is r squared t to the 4th, right? Times the 7 Boltzmann constant, whatever. So we can learn about the combined effect of r squared and t to the 4th in this. But this is already a function of t, right? So I know that there are lines of constant radius in this graph, right? So what this tells us is things are getting hotter or cooler or bigger or smaller. So which direction is bigger?
Top right.
Straight up.
Oh, really?
Yeah. So luminosity goes like r squared t to the 4th. So if r goes up, it just goes straight up. The temperature doesn't necessarily change. If it just gets bigger without the temperature changing, it just goes straight up because it just gets hotter.
Yeah, but what if it's super hot and it goes straight up? Wouldn't it have to get smaller because it would have to compress?
If you have a process, yes, that's a good question. So we've got a couple of things that are going in concert. So we have things that are making the star bigger and smaller and hotter and cooler all at the same time, but they function independently. So the size of the star and its temperature are, let's think about them for now as independent variables. Right? So I can increase the size of the star without changing the temperature by changing the convection rule. So that's a really good question. I'm glad you asked it that way. So what are the processes that happen? There's a lot of little things that go on that have really major effects and consequences on the stellar structure. Let's see. I got 15 minutes to go through all this, so I think I'm in good shape. All right. So the first thing that happens is the hydrogen. Actually, I'm going to write over here what happens. Actually, let's pause for a moment on everything that I think that we know. So put this over here so that we. Oops. Put this over here. I want to not have you in the shot. Okay, so the first thing that happens. So how does this 5 solar mass star die? So there's a couple of processes. The first thing that happens is, in all of this, we're going to talk about two different parts of the star. We're going to talk about the core and the envelope. And that's all below the atmosphere. So the envelope is like the bulk of the star, and the core is just the central part that's really, really hot. So the first thing that happens is hydrogen burning in the core fails. Why does it fail? Because it runs out of hydrogen. So once there's not enough hydrogen, then you can't be burning anymore, and I have a mostly helium core. Now the helium core isn't burning. So by my second equation, since epsilon is 0, DLDR is 0, the luminosity gradient is also 0. You're not making any light anywhere in the interior. That means also the temperature gradient is also 0 in the inside of these cores. So because there's no burning, there's no light, we have constant temperature, and it's going to contract. And start helium shell burning, hydrogen shell burning. Let's see.
Where does the H for the H shell come from?
The helium shell. So it's all hydrogen, and then I have a core of helium, and then there's hydrogen on the outside here. But this stuff is really hot, so this stuff will start to burn in the shell.
Okay.
So it's like if you think about just a pile of I don't know, fuel. It's burning from the bottom. It burns up and turns everything to ash in the inside, and then you're left with just a shell.
Hydrogen simply cannot reach the core because it's like helium is too heavy
That's
because
right.
of the densities.
Yeah, that's right.
So is it just contracting because there's no radiation pressure anymore?
That's right.
And so gravity just, and then temperature increases as it
That's right.
contracts?
Exactly right. Exactly right. So now we have this contraction is Kelvin-Helmholtz contraction. So this is just the gravitational binding energy getting radiated away as heat. So the core contracts, then we get the shell burning, and the envelope expands. But it also cools. The envelope cools, so the surface gets cooler, gets a little bigger, so it's cooling and getting bigger, so it moves in that direction. So it moves up in this direction.
That's on HR9 here.
What's that?
Would there been up that direction or that direction? Yeah.
Is that direction of the HR diagram. So things got to move up in this direction. And then we start, then we enter the subgiant branch. And the subgiant branch is when the helium shell really starts burning. So, okay, it cools. So, okay, as it cools, what does the opacity in the envelope do?
It gets greater.
Decreases.
It was like T to the minus 3.5, it goes down, right? So cools, kappa wait a second. Jesus Christ. It cools, so kappa, which goes like to the -3/5, kappa goes up. I think I might have said it backwards just a second ago. Kappa goes up, and it's more opaque.
Okay, so you can't see through it as much.
Yeah.
Okay.
So you can't. So you can't see through it as much. So the heat can't escape as much.
Mm-hmm.
So the bottom gets hot.
I thought hotter things were more opaque.
No, it goes like T to the -3/5.
Okay.
So the opacity goes down with temperature.
Okay.
So, but it is it's a complicated function. So the average goes down. Various lines will go up. So some things will become more opaque.
Oh, okay.
So some lines will become more opaque as you get hotter, but then get less opaque as you get hotter than that. So this is a complicated dance, which is why I rambled about it being complicated. So as it cools, the opacity goes up. That means the bottom of the envelope gets hotter. So you start to have a convective envelope. Okay, so now I have this convective envelope. Now I start to have convective motions here, which means I can start to bring up some of these lower burning products and bring them up. And I can bring up fresh hydrogen and bring it down. So I can mix. And this is what this first dredge up is. So at the end of the subgiant branch phase, we dredge up all of this helium from the lower parts of the helium core, and we dredge it up into the burning regions, and it can start to burn. So then we enter the red giant branch. So then we get first dredge up. They call this dredge up because you've got, once it gets cool enough and it gets opaque, then it starts to convect, and then it starts to bring up the ash from the burning. So helium we refer to helium as ash from the hydrogen burning. And carbon is ash from the helium burning. So after the first dredge up, then it starts to burn helium. So once we start burning, helium shell burning starts in the red giant branch. So then this gets hotter and hotter and hotter and hotter and hotter until we hit this point where the triple alpha process. Sorry, this is the red giant branch phase. And then the tip of the red giant branch phase. And this is actually a super interesting piece of physics. So the tip of the red giant branch is where the triple alpha process turns on. So alpha. And remember how I said it's a super, super sensitive function of temperature? It goes like T to the 41, right? When it starts, it really fucking starts, right? As soon as it goes, it just all goes because all of a sudden it's hot enough for everybody to get in the party, and then you have this helium flash, which probably doesn't make it out of the star. So you have all of a sudden all of the helium in the core gets burned. In the core, it's really fast, and it heats the crap out of the star, so then it goes back down because it cools and gets bigger. So it goes back down the way it came up, and then it moves over onto this horizontal branch. So the horizontal branch is helium burning. So this way out is when helium is burning in the core. And then the helium runs out, and Kelvin-Helmholtz contraction brings it back to where it was. Does that make sense? So helium burning in the core. Then we move to the horizontal branch.
Sorry, you said that it cools down, but isn't moving left. heating up. So it's heating up after the helium flash.
Oh yeah, sorry. The helium burning starts and it gets hotter. It gets dimmer because it contracts. It gets dimmer because it gets smaller.
While it starts.
Because
it hasn't reached a certain
after so there's the helium flash and then it contracts.
Yeah.
And then the helium burning goes. So we have the horizontal branch, which is helium core burning. And then it moves back. Once the helium is exhausted. This board sounds really weird. And then we have the same process where we start to have helium shell burning. So now we have this core of helium burning ash. What's helium burning ash? Carbon. So we have this core of carbon and oxygen. Because it's easy to make an oxygen. Once you have a bunch of alpha particles, it's easy to make an oxygen from carbon, right? That's just one more alpha particle. So we have this carbon and oxygen in the center, and then we've got helium in a layer out here, and that starts to burn. And then that becomes the asymptotic giant branch.
So by now we don't have any hydrogen?
Well, okay, hold that question.
Okay.
Because where are we in the star? There's still probably hydrogen out here, out in the upper right reaches of the star, in the upper envelope. There's probably some hydrogen, but not always. So in some stars, all of that hydrogen either gets blown off or eaten, but not yet. So there's still some hydrogen.
Still some hydrogen.
Eventually the hydrogen will go away. Eventually in some stars the hydrogen will go away.
In other stars?
Was that?
In other stars?
Depending on the size and the
Okay.
winds. So once you get up to the in the upper reaches of the asymptotic giant branch, we have several processes where the star will expand and the opacity will go down. It will cool, contract, the opacity goes up. It'll expand, and so it has some pulsational phases where you have a relationship between the temperature and the opacity. And then eventually that all runs out and you're left with a carbon-oxygen core at the center. So we have this process of doing all the helium burning of everything that you can around here, and then it starts to launch winds. And the winds make a planetary nebula. Which, the book has some really terrible pictures of planetary nebula. We can find some awesome ones in like 9 seconds of Google. Are you guys, has anybody not heard of a planetary nebula? Everybody totally in love with planetary nebula? No? Okay, let's look at some. Did you have a question?
Yeah, how fast does this all get expelled? I don't really remember.
Yeah, what's the time
I
scale?
don't really remember the time scale for like low mass.
Long. I don't know the numbers off the top of my head.
Okay.
But there's a big table, so it depends on the mass. It's very sensitively depends on the mass. So planetary nebula are these magnificent, and again, this projector is terrible. Give me a good image. Give me a good image. There you go, yeah. All right. Don't everybody fall asleep on me. So these are planetary nebula. So what's going on? And I believe, I just learned this, every one of these is a binary star, which I didn't know until Massimo told me like a week and a half ago, that all of these are binary stars, which makes everything make more sense. I'll tell you why in a second. You have all these crazy patterns, like this one's like 2 rings, like that. This one's like a splat. This one looks round, kind of. This one's pretty round. But a lot of them are really not round. They were called planetary nebulae because they kind of look like big fluffy planets when they first started seeing them, and because astronomers are doggedly refuse to update their terminology. We keep calling them planetary nebulae, even though they have nothing to do with planets. If there was a planet, it probably has been destroyed by now. And then at the center is a carbon-oxygen white dwarf. And that carbon-oxygen white dwarf will just stay there until the heat death of the universe, unless it's got a companion where it can feed. And then it can blow up, yeah.
It's carbon and oxygen?
Yeah. Yeah, carbon and oxygen are the endpoints of helium burning. So it'll make both.
I just thought it was like a degenerate carbon core.
Oh yeah, oh man, I totally didn't talk about degeneracy pressure in here at all. So in this process, so we have this complicated process of the burning stopping, but also at the end, it's supported by degeneracy pressure. Which comes up a couple of times in this process. There's a couple of times where things get very, very dense and it's held up by the electrons and hating each other. So degeneracy pressure is the process by which you can't pack 2 electrons into the same part of phase space. So you can only pack 2 electrons into a given volume of phase space. Phase space is position and velocity, so that means if I've got a bunch of electrons and they're all going a certain speed, I can't add another one that's going that speed. It has to be going faster.
So sorry, this is
Yeah.
way off topic, but do neutron stars just overcome the degeneracy pressure until like they pack all the electrons into neutrons?
Yeah, and then they have another degeneracy pressure with the neutrons. Okay, more later. So I'll pick this back up after Turkey. So come up with homework questions and questions that you want to talk about for the final, or for the next test. There's a test on Friday. We'll review it Wednesday. There's a homework due Wednesday. I'll see you tomorrow in office hours. Is that everything?
Do we still have normal office hours on Thursday?
Probably, unless nobody wants it.
Maybe.
But I figure there's a test the next day, so I'll be around.
Oh.
Yeah. Ah, thanks.
Let's check the time.
Yeah.